Okay, so this video is going to be about the generalized Chinese remainder theorem. And the Chinese remainder theorem is a really important theorem that we've already used some. And so the number theoretic version of this theorem, which is used in cryptography, it's really used all over the place, would be like this. It would be suppose, let's see, let me try that again. Suppose n is equal to m times k, where these are relatively prime, right? So the GCD of m and k is 1, all right? And I'm even going to generalize this in a bit more in a minute. Then what it says Zm as a ring, Zn as a ring, is isomorphic to Zm cross Zk. Now we've seen this for groups, but now I'm saying that this is true for ring, and actually the proof we used even with groups probably use the Chinese remainder theorem. This was something that was talked about in chapter 0 of the book, if you if you remember back then. More generally, right, if n is factored into like n1 through nk, where these are all relatively prime, right, pairwise relatively prime, so GCD of ni nj is 1 for I not equal to j, right? So they're pairwise relatively prime. Then the same sort of thing happens. Zn is isomorphic to Z m1 cross dot 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 cross Z and K. And the proof is really kind of inductive, and it's useful to look at in this case because it'll be it's how the general one goes. And the point is this, that if this is true, right, then it actually turns out that if I define Ni to equal the product of little n j not equal to I, right, then the GCD of Ni and Ni. So this is the product of everything except I, j not equal to I, right? This thing is equal to 1. So those are actually relatively prime, right? So what we have is we have Zn is from the previous theorem, right? Zn is isomorphic to Z Ni cross Z Ni, right? And then we just sort of use induction on that, right? Then we split that up and we keep going. Kind of more to, and another interesting point here is the way we actually get the embedding to be. So the fact that this is a homomorphism is going to turn out to be easy. The fact that it's onto actually is the harder thing. So yeah, what is the map actually? So the map is actually just m, some m less than n, is going to get mapped to, in the general case, right, to m mod n1, m mod n2, right? You just keep going like that. M mod n, what do I call the last thing? Oh, I shouldn't call it n up here. This is so bad of me. This should be like k, right? nk, right, like that. So in the case with just two things, because again, we're sort of getting this from the case with two things using that same trick. So what this looks like is this. I have Z mk, where those are relatively prime, is isomorphic to Zm cross Zk, right? What I'm saying is that the map is, let's see, now I got to use something other than m. So something less than m times k, so let's say j less than m times k, is going to map to j mod m j mod k. And then how do you actually see that this is onto is a little bit is the interesting part here. And the point is that let's see, I'm not even sure if I'll remember how to do it, but since these are relatively prime, we have x m, maybe I'll remember, yn yk, sorry, is equal to 1 for some yk. Y and k, y and x, x and y, for some x and y. you know, in integers, right? Everything's in integers here. And then let's see, what I want to do is I want to say, I'm gonna pause this for a second, right? Okay, pause for a second, coming back. So I want to look at AB in Zm cross Zn, right? And what I'm going to do now is I'm just going to say, well, A, right, is equal to AXM plus AYK, right? Because I'm just multiplying this thing by A, and B is equal to BXM plus BYK, right? And then what I can do is I can look at, you know, some C, right? And I want the result to mod M to be A, so I'm going to call this BXM plus AYK, right? And so let's see what happens. So C mod M, right? Well, that part will just go away, and so this will be AYK mod M, right? But what is AYK mod M? So now we look up here, right? And AYK mod M, so again, we mod out this by M, that part goes away. So AYK mod M is actually A mod M. So this is equal to A mod M. So you see how that trick worked, right? And then C mod K, right, is equal to, again, so that part goes away, and we get BXM mod K, right? But then we look here, right? If we do BX, so we look at this, right? So if I look at BXM mod K, well, that part goes away, and I get that's equal to B mod K. All right, so what I did is I created a C, namely like this, right, which is in ZMN. You got to think a little bit about why that's in ZMN, and if you want to, you could just even take this thing and then mod out by MN. I think maybe I do that in the proof. And what you end up with is, you know, C gets mapped, right, to C mod M, C mod K, and that turns into AB, which is what we wanted to hit. Right? So that's how that proof works. Okay, now I'm going to do this in more generality, not using the modular arithmetic, but using arbitrary ideals, right? So that's the idea. Okay, so what is our, so first, like, how do we generalize things like relatively prime and stuff like that? And so the definition, so it's right here in the notes, right, is that, so I have I and J subset of R, and I and J are relatively prime if and only if I plus J equals all of R, right? So it's like that. Now, what does this have to do with sort of relative primeness in the integers? Well, if you know, because of Bezo's theorem, right? You know, if I have A and B relatively prime, so this was if and only if, you know, there exists an X and Y. We just use that above there. There exists an X and Y in Z, right? Such that X A plus YB is equal to 1, right? But this is if and only if. Now think about these principal ideals. It'll be A, the ideal generated by A, which is, you know, XA for any X and Z, right? So that thing, plus B, right? So that's the set of all YB for any Y and Z, right? So if I look at the sum, well, it certainly has this thing in it. So it has 1 in it, so it has this, right? But the ideal generated by 1 is all of Z, right? So we get, I mean, just sort of following that through, we get that in Z as the ring, right? A, B as ideals now are relatively prime. If and only if, by definition, A plus B equals, you know, everything Z, right? If and only if, right? GCD. Well, I mean, this says there isn't. I mean, what this says, right? I mean, literally unpacking this is, there exist X and Y, because one has to be in here, such that X A plus YB equals 1, right? And so this is if and only if GCD of A and B is 1, right? Which is saying that they're A and B are relatively prime. So that sort of gives you a reason for saying this is a reasonable definition for relative primeness. We haven't actually said what prime ideals are yet, and sort of getting relatively prime. Anyway, that maybe trying to push the algebra too much to get this, but this is kind of the idea here. It's and more importantly, this is what works for what we need. Okay. Let's see. That kind of stuff is discussed right here. I just want to say here's a few more things about relating ideals in general to ideals in Z, right? This is going to be a common thing to sort of keep you want to build some intuitions, and using your intuitions of Z are good. Not all rings are like Z, but some very important rings are sort of like Z, right? In particular, rings of polynomials over fields, right? And that's kind of the main subject for a lot of what we're doing. Notice that A divides B as integers, right? If and only if the ideal generated by B is contained, right, in the ideal generated by A, right? So it kind of flips the order here, right? Because what is this saying? It's saying here that B is contained in here means that there's something I can multiply A by to get B, but that says exactly that A divides B, right? And then A plus B is equal to the ideal generated by the ideal generated by the GCD of A, A and B, right? So that's because if you look at the set of all x y plus x a plus y b, I think this might be the proof in the book, such that x a plus y b is greater than or equal to 1, right? And call this set A, for example. And if you look at min A, it's sub D, and this is equal to GCD of A and B. I think this might be the proof that was in the book, actually. Or you could work it out some other way, but that's sort of what happens here, right? So I mean, looking at the set of all things such that this happens equals something, not D, not necessarily. Let me call it something else, R, right? So there's lots of these R's, right? In particular, our proof of the Bezo's theorem sort of showed that we got every remainder while doing some computation of this form, right? But in particular, D, the GCD is the smallest thing we can get like this. Let's see. I mean, maybe it's important to say. Yeah, never mind. You can say a lot more stuff, but I won't. The ideal. So we take the ideal generated by A and the ideal generated by B, and we take their product, right? So it's generated by what? It's generated by products of things from those. Well, these things are just XA, YB, so it's just something times A, something times B. So this is generated by a single thing AB, right? So that's important, right? So the product of these two ideals is just that thing there. On the other hand, the intersection is the LCM, right? Because let's see. So why is it? So first of all, let's think about the order here, right? So we have A intersect B, right? Let's say, let me get this in the right order, is contained, right, in A, and is contained in B, right? Now, by the way, we know something we'll prove later is that whatever this ideal is, it is generated by a single thing, C. Okay, so that's part of being a principal ideal domain. We're going to prove that later on. But in particular, looking at the thing that we had above, right, this means that A divides C and A divides, and B divides C, right? So whatever this C is, right, C is actually divisible by both A and B, right? So it's certainly a candidate for the least common divisor of A and B, right? And it's also and then you can show that this thing has to be in this. I mean, it's clear that this is in here, right? Because whatever LCM of A and B is, right, it's something times A, and it's also something else times B, right? So it is in both of those things, right? So this is generated by that, so that gives you that. And this gives an example, right, where so just putting this together, because we have, okay, LCM. Sorry, I want to get the order right here. Okay, so I have here so AB, the product, right, is equal to a B, right? Generally, it might be the case that the LCM of A and B divides AB but isn't equal to AB, right? So is less than AB in particular, right? So this would say this is now contained in, right? This LCM of AB, and so this is equal to A intersect B, right? So generally, A intersect B can be bigger than AB, specifically when the LCM is not the same, right? So in fact, what we get here, right, is we get that AB equals A intersect B. Oops, the ideal A intersect if and only if A and B are relatively prime. So I could say if and only if A plus B, you know, A and B as ideals are relatively prime, right? So we could do like that. So anyway, lots of good, sort of number theory stuff. And now we want to get the same sort of thing in general rings, right? So let's see what we can get, can't get. So let's see. So what's not generally true? Let's see. What do I want to say here? Do I want to say all this stuff? Well, okay. Let me just write. So let's see. What do I want to say? Why do I want to say it? I guess for some reason I do want to talk about this. Okay, so I say, I'm just going to write down what I want to say, and then when it comes up and is important, I will have it. Right. Remember, so this thing, so in our looking at the stuff above, right? So this would be the GCD, sort of again, going back to our similarities with what we did above, this would be the LCM of A and B, right? And so this would be AB in the integers, right? That is true, right? So in the integers, it's true that if I look at the ideal generated by A plus the ideal generated by B, that's this one, right? And I look at the ideal generated by A intersect the ideal generated by B, right? That I get the ideal generated by AB, right? Again, that's just using number theory. So it's not generally true here that we get this, right? I mean, so, well, I don't want to say it's not true. What I want to say is it's not generally true, right? So what is true? Let's see what is true. We do have that I plus J, I intersect J, right, is equal to, now we can distribute, we know that from earlier stuff, I intersect J plus J, I intersect J. And remember, we don't have commutativity. Actually, no, I'm saying in commutative rings, right? So here I'm in, so R is commutative. Right, so in that case, right, I have this. I mean, I haven't used commutativity yet, right? But then this is contained in. Well, this is certainly contained in IJ. This is certainly contained in JI, right? And in the case that we were commutative, this is the same as IJ, right? The order wouldn't matter, right? So that's where I'm using the commutative property here, right? So I'm saying if the order doesn't matter, right, then I get that. So what I'm getting in general is this kind of subset relation like that, but not necessarily equality, right? Which is good, right? Because we only got equality here. Sorry, I keep confusing myself. We only got equality here. Yeah, we only got equality here. No, we always get equality there. Yeah, I'm getting myself confused. Okay, anyway, so just let's go on and see what I use it for. Okay, so I want to do something here. What do I want to do? Yeah, okay, I want to do this. So if I and j are relatively prime, I and j are relatively prime, so I know that I plus j is r, right? Then I can argue as follows. ij is contained in I intersect j. That's always true. And this is certainly equal to r. I have a unit, right? So I can always just multiply by r. So ij, right? So I mean r as a ideal acts as a unit. We talked about that earlier too, right? And so this is I plus j times I intersect j. This is why I needed this computation above. Okay, and we just showed that this is contained in ij, right? So what we're getting, just to recap, right, is if R is commutative plus unity, right? Commutative ring with unity, and I and j are prime, relatively prime, then let's see, what am I getting here? Oh yeah, ij. The main thing I have here is ij equals I intersect j. So in that case, right, we get this, right? So that's awesome. Because, okay, and what is this saying in terms, like, again, comparing it back to number theory, this is like saying AB, right, is equal to LCM of A and B, right, if and only if A and B are relatively prime, which we know to be true. Right, so it's that kind of equivalent statement, right? So we're getting that equivalent thing for ideals in general, as long as we're in a commutative ring with unity, right? So that's the situation we're in here. Okay, so I have a little proof of that thing there. And finally, we get to the theorem, right? So here's the theorem we finally have. So here I'm not assuming commutative ring with unity. I'm just assuming that I have two ideals that are relatively prime. Okay, let me just scroll up a little bit more. And so I'm getting that I can get phi. Yeah, what I'm claiming here in this thing, right, is that R over I intersect J, these are relatively prime, is isomorphic to R over I cross R over J. Right, so that's what I'm claiming here, okay? And the way we're going to do this is we define phi going from R to R over I cross R over J. Now, this is the proof of the, sort of step one of the proof of the Chinese remainder theorem, but this is the main step. And so phi of R is simply defined as R plus I, R plus J. This should look familiar to what I did above, right? So it was like if I was taking Z, right, and mapping it into Z M cross ZK, right? And then I'm going to show that the map has kernel equal to Z MN, right? And then, sorry, that's not quite right. I get, sorry, the kernel is equal to NMZ, right? And so then you apply the first isomorphism theorem and get that Z over NMZ, right, is isomorphic to Z M cross Zn, right? And this, of course, is isomorphic to Z sub NM, right? So that's what I had up there before, right? So this is the same thing, but with ideals here, and I don't quite have the corresponding thing here yet, right? So I have something slightly different there. Okay, so let's just see the proof. Okay, so again, right, phi is going from R to Ri cross Rj, right? The map is mapping R to R plus I, R plus J. I've got 5 minutes. I don't know. We'll see what happens here. Right, so I want to say phi is surjective. This is the same proof I gave you above, okay, but now in this case, right? So the point is I plus J, right, equals all of R, right? So I'm taking something in here, right? So I'm taking like r plus I, s plus j, right? So that's like an arbitrary pair, right? And ri cross rj, right? So different r and s perhaps, right? So that's kind of the point. And I have this, right? I have a ring with unity, right? So I have some a and I, b and j, such that let's say I need some. So let me just say xa plus yb, right, is equal to 1, right? In fact, no, I don't even need that, right? Sorry, don't even need that. Doing something. I'm even going to do this a little bit better. Because I know this, right? I have that r itself is equal to some ri plus rj, right? Where this is coming from I and this is coming from j, because I pick up everything, so I'm going to pick up r. S is equal to si plus sj, right? Because s is in r, so it's coming as a pair like that. And I'm going to put these together, right, by taking, how do I want to do this? Yeah, I mean, so let's see. So those are there. Oh yeah, I want to take C equal to, I shouldn't look at my notes. I should just do it, because this is exactly what I did above. S, J. Yeah, I'm going to flip it around. C is equal to RS plus SJ. That's what I just wrote. Sorry, let's try that one more time. Oh, gosh. C is equal to RS plus S, not RS, RJ plus SI. That's what I'm trying to say. Okay, now let's see what happens here. So C plus I, right, is equal to RJ plus SI plus I, right? And what is SI plus I? So I'm gonna, sorry.